Good morning to all gathering here. A warm welcome to our today's resource person, Dr. C.K. Bablal sir, professor from EEE Department, Yarada College of Engineering. Sir has vast experience both in academic as well as research. Sir is guiding number of research scholars. They publish their research work in various reputed journals. Once again, I welcome you, sir, for this first session of fourth day of this Atal FTP. Now I request Mrs. Ganesh Kumari ma'am to give brief introduction about our resource person, Dr. Babla sir. Please ma'am.
It gives me a great pleasure to welcome all of you. Good morning, everyone, and welcome to today's session. On the behalf of KLNCE Atal FDP, I extend a very warm welcome to our resource person, Dr. C.K. Babulal sir, Professor, Department of EEE in Tyagaraja College of Engineering, Madurai. I would like to introduce today's speaker, Dr. C.K. Babulal sir. He has completed his BE degree in 1991 and the ME degree in 1993 in Tyagaraja College of Engineering, Madurai. He has completed his PhD degree in the year 2007 under Madurai Kamaraj University, Madurai. He has 27 years teaching experience. He is currently working as a professor, Department of EEE in Tyagaraja College of Engineering, Madurai. He is a recognized supervisor under Anna University, Chennai, and he has produced 8 PhD scholars and guided 30 ME scholars, and is currently supervising 3 PhD research scholars. He has published in international journal around 35 journals and 15 conference papers, and has delivered 45 special lectures and has done 3 sponsored projects. He has organized 2 faculty development programs. He is also a reviewer for 19 international journals and has received Outstanding Reviewer Award in Renewable Energy and elsewhere. He is a member of Board of Studies and member of PhD Selection Committee, member of Inspection Committee, and he is member of Staff Selection Committee for various institutions. His area of interest: power system voltage stability, artificial intelligence applications to power systems, and power system restructuring. Now I hand over the session to Dr. C.K. Babulal sir. I once again welcome you, sir.
Thank you very much.
Thank you, sir.
Better you can put your audio in mute so that other could be able to hear very properly. Let me put my screen. Once it starts showing, we will start. I hope you could be able to see the screen.
Yes, sir. Visible, sir. The screen is visible.
Thank you very much. Very good morning to all. At the outset, I would like to thank the AICT for sponsoring this faculty development program. I thank the organizers of this FDP, especially Nyanambal Madam, Vimala Rani, and other people who are involved in this FDP. Hope the participants would have already attended 3 days of program. Maybe in the first day you have got a very good introduction to the smart grid from MP Selvam sir. And our objective today is to see how optimum power flow can be implemented using PSO, and the objective is to introduce demand response in smart grid environment. So we have enough time to take the introductions and see the logic behind it and how to apply this, and the results we can verify. I think this is a good opportunity for participants to get wide variety of information. So wherever I go for FTP like this, I would like to give a brief introduction about what is electrical engineering or what is power system engineering. Especially it is a smart grid environment. So whenever you meet students of electrical engineering discipline, maybe any year of students from first year to final year students, so I think you can give some important thing that is in our country or in general, maybe useful for you and for others, right? So it is may not be available in books or anywhere else. So by years of experience and by collecting information, it has been developed, right? I think now we can enter into the topic, right? So I will take some time to see what is history of electrical engineering and then how the power system has been evolved throughout the world and in Indian context, and then what is power flow studies and economic dispatch, then how optimal power flow came and what are all its formulations, then how to use PSO for optimal power flow. So these are all the content for the morning session, session one. And then the afternoon section, maybe after the first session, what we will see is mainly the demand response, right? So what is demand response, how it is introduced, what are all the objectives, what are all the classification, cost, measurement, and everything in a detailed manner, right? uh, Maybe I have given a very comprehensive way that suppose if you are guiding your PG scholars, you can also ask them to work it on this area for their thesis, right? You can ask them to modify something. And also I have attached I have given the link for MATLAB programs. So whenever you get time, you can download it and you can use it. You can run the program, PSO program, and you can verify the answers. So those things are available in the second session, right? So let me enter into the morning session with the introduction of history of electrical engineering, right? So I think there are two figure, very important figure. Of course, the man in the right, you can very well-known face for electrical engineers, right? So I used to tell he's the father of electrical engineering, right? Because he only developed the public usage of electricity to the people. So though it has been electricity has been developed in many ways, but for the commercial usage, he is the only person, and we should be very proud. He's an electrical engineer and best businessman in the world. And you can see in the left side a diagram of Pearl Street Station. This is the first place where electricity is generated, right? So Edison uh, there is a small mistake, sorry. Edison developed the first electric power station at Pearl Street in New York of Manhattan City. It was only incandescent lamp, so it looks like pearl in the evening. That's why it is called a Pearl Street Station, right? So even today it is called a Pearl Street only. It is the Manhattan city of USA, and you will see that it's only around 140 years, 138 years old. So the age of electricity is less than 132 years for the commercial use, right? So the first system, that is the first power system introduced, was a DC system. So unlike most of people, we think that it is AC system. but it is not so, right? So Edison introduced a DC system to the people. There were only 59 customers, and the specification of DC voltage is 110 volt. Even today, in USA, 110 volt AC system is followed. Why Edison chosen 110 volt for his supply is he invented a incandescent lamp. In order to lamp to ignite, it needs 110 volts, right? That's why he made as a standard, right? So he wanted to sell the incandescent lamp to the people. So who will buy without electricity? So he wanted to sell electricity to the people. So he created a generating station, dynamo. He used a DC system. So 110 volt has been designed. So later on, in order to avoid changing the infrastructure, people have started using 110 volt. The radius of the length is only 1.5 kilometer. So he gave capacity to uh, customers of around 1.5 kilometer length. So he could able to successfully give. After seeing this throughout the world, many people want electricity. So everybody started almost in the same period. Everybody started uh, using a power system and giving electricity to the people. And Frank Sprague, who added motor loads in the 1884, before that only mechanical motion has been created using engines, and he is the first man who connected the motor loads in 84. And almost you see that from 82 to 86, Edison has developed a DC system for very large customers, and he found that DC cannot be transported to long distance because of loss in the system. So loss in the transmission line makes it's unviable to transfer the electricity to the longer distance. So in between, there was a testing was going on using AC power system by Goulart and Gibbs in Britain, and the practical transformer developed by William Stanley. You can see in the left, this is the photo of William Stanley. Almost stops the usage of DC system and the birth of AC system. And it is mainly because of the Nikola Tesla. We can call him as the father of modern power system, because he has developed the three-phase system, polyphase system, and he only advocated the AC induction motor, AC generator. Almost he has more than 250 patents for his inventions. So even today we use only the power system developed by Tesla. So I think the modification only in only the measurements and a little bit usage of fax devices. So the system developed by Tesla is the three-phase system, and still it is being used. So that's why we can call him as a father of power system. And there was he was a very poor researcher, and in order to get the money, what he did is he sold all his patent to Westinghouse corporations, and Westinghouse Corporation wanted to promote AC system. So actually there was a Cold War between Edison and Westinghouse Corporation. Edison has a company, Edison Company, or General Electric Company, and Edison Company wanted to promote DC system, and Westinghouse Corporation wanted to promote AC system. So there was a Cold War between Westinghouse Corporation, especially Tesla and Edison. The first AC power system was introduced in the year 89. almost you see that 8 years he successfully give electricity using TC system. In the 8 years, he used to give supply only in the evening, and there is no stability problem in the Edison power system. So that was the great thing that even in 1890 you could able to give a reliable power, and we can see that. In 93, the three-phase system was introduced, and after 1890, Edison also thought that DC cannot be continued, so he also went to AC system. Before that, he was done so many things to threaten the people not to go for AC system. He used to take AC is very dangerous, and you can see this slide. It's a very old slide taken from the internet. It shows the current war between Edison and Tesla. Tesla wanted to advocate AC system, and Edison was supporting DC system. So Edison threatened the people of American by killing the street dogs with AC. So what he will do is he kill the street dogs and tell the people that threaten the people that not to go for AC system to the height of it. What he did is he killed an elephant using AC system. So he will do anything for getting business. So unfortunately, he cannot sustain because of the development of a transformer. Right? There is no way to increase or decrease the DC voltage. When he wanted to give electricity for more than 30 kilometer, he unable to do with the transformer. Tesla was able to do, and there is no stoppage for AC system. But recently, with the development of solar power, DC system is again regaining around the world, and some part of it people were there are using some DC fan also. So maybe the scenario may change after this, right? So these are all some of the history about DC and AC system. And participants, if you wanted to ask any question, you can interrupt me at any time. So when I put the PPT in a presentation mode, the difficulty is that I could not able to see the chat box, right? So one can alert me to see the chat box for questions, because when I put in the presentation, nothing is visible to me. But chats are visible to you, but I cannot see. So I have to switch over to the chat. So maybe if you have some question that you can raise in the chat box, and you can alert me to see the chat box, so that will be easy for me to know that you raised a question, right? So
Sir, sir, we
yes,
will
ma'am.
help you, sir. If anything in the chat box, we will help you, sir.
I'm not getting you, madam.
Sir, sir, if anything in the chat box, we will help you, sir. Sir,
No.
am I audible, sir?
Your audio is very poor, madam. Unable
Sir,
to
if any queries in chat box, will inform
Okay,
to
you
you, sir.
inform me,
Okay,
madam.
thank
Okay.
you, sir. Okay, sir.
Okay. Thank you, ma'am. Thank you. Right. I will continue with that. So around the world, everybody has started using electricity, and there were no standard, because everybody create on their own way. So you see that there are so many frequencies around the world has been used. 25, 50, 60, 125, and 132 3 hertz frequencies were also used. And then when the power system became larger and larger, they wanted to interconnect different power systems to improve the reliability. So people have thought of having a same frequency only you could able to interconnect power system. So thought of introducing standards. So that's why throughout the world, everybody wanted to use 50 hertz frequency, and most of the country uses even today 50 hertz. And USA, they wanted to be different from others, so they used 60, and some countries supporting US also uses 60 Hz. So throughout the world, there are only two frequencies have been followed today. And again, there are many voltage transmission voltage throughout the world, and it goes on increasing like anything, exponential increase. So in India too, we have a very old system, 50 or 60-year-old transmission lines we are using. Because it was old, we need to operate at the same voltage. Then you see that in 1966, 735 kV hydro evoke in Canada, they have used 735 kV in 1966 transmission voltage. It's a really very you see that it is almost 60 years before. Maybe now I'll ask one question to the participant. What is the maximum transmission voltage in India? Can anybody put it in a chat box so that I can see the answer? 1200. Chaitanya says it is 1200. Okay, good. Any other answer? 765 kV, very good by Madhu. Good. Any other answer? Rajinikanth says 765 kV. Okay, good, right? So, and I will ask 1200. I see that Andhra Pradesh teachers are telling it is 1200 kilovolt, and Tamil Nadu people are telling it is 765 kV, right? So, today it is only 765 kV only. Anybody know when this 765 kV was introduced? Anybody? Okay. For many years in India, 400 kV was the maximum transmission voltage for many years, right? Only before 5 years, only 765 kV transmission was introduced, and there was a strong research is going on for 1500 kV, right? So in India, there are so many 765 kV power station. In Tamil Nadu, we also have two power stations of 765 kV. Right? We will continue the presentation. Okay. I think it will be convenient. I can ask question like this, and they can answer me. So it will avoid the one-way communication. So it will be interesting to meet you in the chat box often, right? So you see that US has tested 765 kV in 1969, right? Then the HVDC was developed, and a long submarine cable was connected in the Sweden. You see that's a 96-kilometer HVDC line was introduced, and these are all the scenarios of the world context, and let us see something in how power system has been developed in India, right? So you see that somewhere around 1882, the first power system came in the world, almost in 1891 or something, right? So they have started, and they wanted to introduce the first power system to the capital of India, and British people wanted to develop Calcutta, and they wanted to bring Calcutta as the capital of India, but somehow it has changed. So almost you see that all introduction were came only in Calcutta. So the first place in India to get electricity is Calcutta, but the success of electricity came only in Mumbai. That is in the way of the electric tram. So the Bombay Suburban Electric Best is started in the year 1905. See, it's more than 115-year-old electric power train system. So I think it is one of the best in the world for using electricity for mass transport of people. And Tamil Nadu in Chennai also the first electric train has been introduced, and it was in history that electric train was earlier has been introduced in Tamil Nadu too. The Bombay's VT Kurla is the first station to get electrified in India, and then the electrification for meter gauge in 1931 between Chennai, Madras Beach and Tambaram. Till today, it is a very, very famous electrical gauge. And we'll see that for many years we have 5 different regions of electrical. The electricity has been divided into 5 regions in India. It was called Eastern region, Western region, North region, Southern region, and Northeastern region, right? So there is no central region, right? So in the map, it shows the all 5 region, and you see that there are why we may wonder there are only thinly there is no population in the northeastern region, but as far as electricity is concerned, the biggest producer of electricity lies in the eastern region of India, because throughout the year they will get a rainfall, so there are many hydroelectric power systems. So electricity is produced in bulk in the eastern region of India, and you see that all the electricity produced in the east must be transported or evacuated to the west. To the nearest large consumer is the Mumbai, Maharashtra. So it is the old scenario. Just I wanted to tell that how the electricity or power system is managed in India, right? So there were 5 regions, and each were separating at the different frequencies, and they have a different schedule. Then it took some years to integrate the regions, and you can see that in the chronological order how they have been added, right? 5 regional grid with 5 different frequencies. Then in 91, eastern and northeast were synchronized to single region, and then 2003 western region also synchronized. Then in August 2006 northern region synchronized, and finally the southern region is synchronized in the year 2014 or 13, right? So in India now we have only one grid, one frequency. I think you would have heard about blackout in many countries. Anybody heard about India blackout? Anybody heard about India blackout? Being electrical, yes sir, okay. Saidanya, good, okay, yes. Sriram, okay. So India blackout means what? Blackout means a complete shutdown of power supply. There is no power stations are switched off, right? So that leads to no electricity for the people, right? So I think we did not experience any Indian blackout so far. We experienced only regional blackout, right? So the last blackout that we northern grid, very good, very good, very good. That was the last northern grid blackout. Do you remember the year when it was the northern grid blackout? Okay, not sure. Okay, nothing. Okay. 2012. Very good, very good. Okay. That was that time the prime minister was Manmohan Singh, right? So even for the prime minister office there is no electricity. Just imagine, no electricity for the prime minister office. Please share the attendance link. Okay. I think now it is not the time to ask this question. Please listen the class, and if you have any questions, you please. I think the organizer you have sufficient time to talk the organizer after this session. Okay. Well, they wanted to. So the Delhi, the Prime Minister office and AIMS also need electricity. Without electricity, many people will die. So they what they did is they procured electricity from Nepal. So they have connected to the PMO Prime Minister office and aims to get electrified, right? So almost northern region and some part of eastern region, northeast also involved in this collapse. So India has a beauty of that islanding operation is even possible today. Right, if anything goes in you see that if anything goes wrong, we can make an islanding operation, and it is possible to separate the faulty portion, and we can survive the rest of the system. That's why I think many of you may not be, I don't know whether how many of you know that 2003 blackout in it's 2003 is the very very worst year for power system engineers, because USA and Canada experienced a very bad blackout. There is no electricity for more than 3 days. Many people have died because of this non-availability of electricity in the US and Canada, and followed in England, Spain, and so many countries have experienced a blackout in those years. And all are developed countries, and they were wondering, they have a very good control system for power system, but they are unable to avoid the blackout. Actually, the team of people from USA came to India, and they are really wondering. We don't have that much technological development in controlling the power system. Even then, we could able to manage our power system with no blackout. So team of people came to India, and they have seen that how beautifully we manage the power system. So the main reason was it was segregated into several regions, and each region has its own responsibility to maintain its frequency. So these were all the some of the reasons, and how it was mostly manual control during that time, and that could be the reason for keeping the system in a reliable operations. Right, I will come back to the slides. So from 2013, we have only one frequency, one grid for the entire country, right? So this diagram shows there are the surplus availability of water in northern and northeast part of India, and the eastern region we have coal reserves. Today almost we have plenty of wind power and solar power in southern region, western region, and so on, right? So there are some interconnection between the other countries also there, between Nepal, Bhutan, Bangladesh, and there is a thought between 1500 kV HVDC between Madurai and Sri Lanka through the sea route. So these are all the some of the pipeline projects, and managing such a large grid of installed capacity of 372 gigawatt is not so easy. We are the third largest energy producer in the world. So the frequency problems and voltage problems are inherent in the power system. It needs to be maintained. Okay. Now we'll see what is the some of the basics of what is power flow solution, and slowly we will build upon optimal power flow, and how can we use for PSO for it. Okay. So the basic question, so whenever I will ask in the test is what is power flow solution or load flow solution, right? Or what is power flow analysis, right? So it is hard to find in any book that, or if you ask anybody what is power flow analysis, maybe sometimes immediately they don't have the answer to tell, right? I think this is the answer that you can note. And the word analysis is the English meaning of analysis is calculation, determination, or finding something, right? Power flow analysis deals with calculation of PQV theta, right? So in power system, so the determination of active power, reactive power, bus voltage, magnitude, and associated angle for all buses are called power flow analysis, right? So please ask this question to all students in all your internal assessment test. We are very familiar with the type of buses, right? The buses in the power systems are classified as generator bus, load bus, and slack buses, right? So we don't put often our effort in understanding what is a slack bus. You ask any utility person. Utility means people working in electricity board, right? So we don't use the word utility, and we will use only the electricity board in our country, but other country people say it is utility, right? So utility is an indicator is electricity board, right? You ask any electrical engineer who works in utility for more than 25 years, what is slack bus? So he may laugh at you because you do not know what it is, right? Only the academician knows what is a slack bus, right? Actually, slack bus is not existing. It is a fictitious bus, right? It is not at all existing. And slack bus is introduced only for analytical purpose, right? So it is not in a reality. So why do you need a slack bus? You are going to calculate. So it's a PQV theta are the four parameters. Among them only two parameters are known at a bus, so the other two makes unknown, so it's very difficult become non-linear to solve the problem. That's why we will make assumption of one, and the losses occur in the system that we wanted to reserve to a particular generator. Usually the largest generator is taken as a slack bus, and there is also a concept of called a distributed slack bus. That is, instead of giving losses to one generator, why don't we distribute it to all generators? So that concept is called distributed slack bus, right? So you'll see that at every bus only two informations are known and other two informations are unknown. This makes the problem become non-linear. So we are forced to assume one. So we will assume a flat voltage profile of 1 plus J0 or 1 of angle 0. Based on that, we will go on iterative technique to produce the solution, right? So the question, what the load flow solutions are optimized? Anybody answer me, yes or no? Is load flow solutions are optimized? Yes, yes, okay, good, very good. Anybody else?
Oh, no.
Yes, yes.
Some participants. Okay.
I'm getting answer. I'm looking at the chat box, right?
Okay, sir.
Okay, thank you. I think I can better explain the question. Optimization means what? It's a process of finding a better solution, right? Uh, it's a process of finding some better solution. So power flow is not optimized solution. Okay. So please, this is the right way to develop ourselves, right? So if you get one information from my presentation, I will be very, very happy. Okay. So please remember that low flow solutions are not optimized solutions. It is only giving the solutions, right? So in power system, there are many possible solutions. There are many possible solutions, right? One of the solutions that we will take into account is load flow solutions. Load flow solutions are not optimized, right? So no is the answer, right? Okay, so optimization means what? When you use load flow, right, it create a balance between generation and load with all constraints. That's all. So it doesn't worry about whether it is optimized solution. Suppose I wanted to get a minimum generation of cost. Load flow doesn't take into account it, right? There is no component for it, right? It's only create a solution that balance the generation and load. Okay, so it is not optimized, right? So the answer is it is not optimized, right? So many solution combinations are possible by scheduling the generation. So economic dispatch is the optimized solution, right? So we'll see what is the economic dispatch, right? So maybe in commitment or another. Okay. Economic dispatch considers that all generators and loads are connected at the single bus. So the objective is to minimize the total cost of generation, and it doesn't consider the network and the transmission lines. So what it will give is it will try to determine the cheapest, it will try to determine the minimum cost of generation by supplying the loads, right? So it doesn't take into account the transmission network. So economic dispatch is an optimization problem. Without considering the network, it will give the minimum cost of generation by considering the generator limits and maybe the operating limits of voltages, right? So limitations, right? So you see that the previous figure shows all generators or loads are connected at the same bus. It means no network is involved. But in practice, right, it is not so. So we have a strong network. The largest man-made system in the world is the power system, right? If you are a power system engineer, be proud and tell your students that the largest man-made system in the world is the power system, because it almost nook and corners of every parts of the earth. You can see the transmission line flowing. So it is the largest network, so you cannot leave away it. So economic dispatch doesn't consider the network, and the solution that you give may not be feasible because it doesn't know whether the voltages that you get is an acceptable range or not. It doesn't give. So Carpentier has introduced an optimal power flow, right? So optimal power flow takes everything into account. That is, it takes load flow into account. It takes all constraints in the system. So it is what I can see is somewhat a superset of economic dispatch, right? So economic dispatch with network consider is optimal power flow, right? So it is an optimization problem, right? And the classical objective function is to minimize the cost of generation, and there are many other objective can also be framed. uh, there are equality constraints and inequality constraints. The equality constraints are power balance at each node, or power flow equations must be solved. So solving the power flow is become the part of optimal power flow. And the inequality constraints are network operating limits, like maximum possible power flows in the transmission lines are called thermal limits of the transmission line, and bus magnitude, load voltages, and the limits on control variables, upper limit and lower limit of generators. And now we'll see how what is the mathematical formulation of optimal power flow. The decision variables or control variables. There are many possible ways that you can choose a decision variables. you can consider active power output of the generator, that is real power output of the generator, can consider it as a decision variable. Depending on your problem, you can consider one or more control variables in this list. So you can consider active power input, voltage at the generating units, transformer taps, position of the phase shifter, status of switched capacitors and reactors, power electronic devices, parameter. We will go to the state variables, and the state variables are the variable that changes when response to the control variables. So the magnitude of voltage at load buses, and we do not take into account the generator because it's a controlled variable, and the angle of voltages at each bus. So these two are taken as state variables of the power system, and you can represent it as a vector of state variables x. Then parameters. There are we need to consider various known characteristics or known information in the power system, namely the network topology, how the transmission lines are connected, the network parameters, namely resistance, reactance, susceptance, flow limits, voltage limits. Anything wrong? I'm getting some hissing noise. Okay, I think there is no problem. I can continue.
Okay, proceed, sir. Continue, sir.
Okay. Thank you, Mona. So you will see that the transmission network parameters becomes the known parameter, and the generator cost functions also known, limits of the generator. So the known information in the power system are called parameters, and you can write it as the vector of parameters as so y, right? So the classical objective function is minimization of total generation cost. You can also other objective functions like minimization of active power losses in the system. Maybe you can have a minimization of voltage deviation in the load buses. You wanted to minimize the voltage deviation. You can also reduce the reactive power requirements, and you can also use a minimization of changes in the control variable, right? So the control variable changes can also be used as objective function, and the classical objective function nowadays is called social welfare, right? The minimization of total generation cost is a old term used in before restructuring or unbundled system, right? So now the today the electricity is restructured. Of course, we have not seen the full benefits of restructuring in India, but it is we have introduced some portions, and we are also experiencing the pros and cons of restructuring, right? So then you can create any objective function based on the requirement. So this is taken into account the minimization of the total generation cost. So it means what you calculate the cost of each generator for producing a particular power output. So CAPA is the cost associated with the generator, and it is a quadratic equation usually that shows the relationship between the power output of the generator and the cost of production. So when you add all generator cost, what you will get is the total generation cost, and the total generation cost must be minimized is the usual or classical objective of optimization problem, right? So these are all the objective function, and you have constraints equation. The foremost constraint is the power balance constraints. The power balance constraints means what? Uh, the generation must be equal to demand at all instant of time, right? Let me ask one question here. Uh, Suppose there is an imbalance between the generation and load, what will happen? Anybody? If generator power is not equal to the demand, what will happen? What problem will occur? I'm looking at the chat box.
Participants, please
Uh-huh.
answer in chat box.
Ganesh Kumar, you need not worry, right? Okay, I can
Okay,
handle
sir.
you.
Okay,
You
sir.
can also
Thank you.
listen like a participant, right?
Okay, sir.
Okay.
Thank you, sir.
Okay. Mm. Frequency deviation. Very good, very good answer, right? Frequency problem will occur. Voltage will lead to no. Okay, there is no voltage problem, right? The power balance causes if the power is not balanced. So at power system, at every instant of time, the generated electricity must match the load. If it is not matched, then you will get a frequency problem. When the frequency will go up, frequency will go up above 50 hertz. When the frequency will go up in power system, participants, those who are listening, load is reduced. Okay, Sivasakti, good. Load is less than generation. Very good answer. Generation is more than load. Very good, very good. When so there is a mismatch between the generation and load. If the generation speed varies, no. Okay. If the generation is greater than demand, you will have a high frequency problem, right? If generation is more than demand, you will have high frequency problem. If the demand is more than the generation, you will have low frequency problem, right? So if the frequency is low, right? If the frequency is low, 50 hertz we wanted to maintain. Let us take the frequency is 49, right? Frequency is 49. Anybody can tell me how can I improve the frequency? What I have to do? I repeat the question, right? I wanted to maintain the frequency as 50 hertz, right? But the frequency now it is 49 hertz, right? As a power system operating control engineer, what action that I can take so that the frequency can be increased? Frequency, somebody is telling answer. Let me check the chat box. Governor control, very good, very good. Steam input to be increased, very good. By increasing the steam output, right? Okay, all your answer says increase the generation. Okay, governor control input, steam input must be increased. So all everything refers to increase the generation. If you increase the generation, you can, or you can reduce the load. Okay, so two solutions are possible, either increase the generation or decrease the load. Okay, so let me come back to the slides and you see that this is a power flow equation, right? So the balance between generation and load is balanced both for active and reactive power, right? So the compact expression for representing power flow equation in terms of state variable, control variable, and parameter is equal to this G. Constraints in the power system, there are, if whenever you have an objective function, there will be several constraints. In power system, you will have constraints like this, that is limits on the control variables. What are the limits? The generation limit. Each generator has its own upper limit, lower limit. So you cannot produce electricity beyond the capacity of the generator. So that fixes the maximum limit. Similarly, you cannot produce the electricity below a certain value, right? That is the lower limit of generation, right? So limits on the generation, limits on the transmission line. So every transmission lines are designed for flow of certain MVA. So there is a limit for power flows in the transmission line. It is called the thermal limits of the transmission line. And operating limits, must operate your power system within the possible ranges of voltages. So thus forms the voltage limits, right? So anybody tell me what is the maximum voltage deviation allowed in the transmission system? What is the maximum voltage deviation allowed in the transmission system? 5%. Very good. Any other answer? 5 or 6%, plus or minus 5%. Very good. Okay. I will ask one more question in this. What is the variation of voltage allowed in distribution system? Plus or minus 6%. Okay. Is it your guess? Point not one per unit. Okay. 12%. Same. Not sure, sir. Good. Okay. We see that's good. Chaitanya says 10%. Okay. Good. You see that every people we speak about only the transmission voltage deviation, right? Is it so? Is it transmission voltage or distribution voltage? It's only transmission voltage, right? So, okay, distribution voltage can be even more, right? It can locally manage it, right? Actually, there is no limitation, right? Instead of 230 volt, sometimes we will experience less than 200 volt. So it is more than, it is even 15% less than the requirement, okay? Actually, there is no standard for maintaining the voltage at the distribution level, all right? So we have capacitors, and the local operators will take into care of this, right? Okay, this is all about the formulations of optimal power flow. So in the nutshell, what I can say, it's a very compact equation is H X U Y, right? So what are the three information that we have studied? We started with the control variables, right? Objective function, constraints, decision variable or control variable, state variables, and parameters, right? So these form the optimization problems, or we call it as optimal power flow. Now we will go to the PSO. So I think it won't take much time for giving introduction to PSO. It's a very easy technique that anybody can easily adopt. Okay, particle swarm optimization. It is based on the population-based stochastic optimization technique. So it's a population-based technique. These are actually developed from the inspiration of how social behavior of bird flocking or fish shoaling. So you would have seen that these are all the picture often in various TV channels, right? So they collectively, birds and fishes collectively try for the food, and eventually after getting food, all will go there and take it, right? So this concept of how each you can call it as a particle, right? Each bird, how it look like that it is always running in the same direction for finding the food, but it is not so, right? Truly it is, each birds are following a different directions and different speed, and it is goes on adjusting its speeds and until they find a food, right? So each will adjust its direction and speed frequently, right? The PSO is developed or introduced by Kennedy and Eberhard. Eberhard is an electrical engineer, and Kennedy is a psychologist. Only it's developed in 1995. You see that it's a relatively very new technique, right? So it helped many teachers to get a PhD even today. So it's only 25 years old logic, right? So the concept behind the particle swarm optimization is it uses a number of agents, right? We call it as particle. So every bird, every fish is called a particle. So each particle is looking for the best solution. Each particle want food, so it is finding the best solution. So the collection of these particles are called swarm. So that is why it is called particle swarm optimization. This concept is introduced in optimization technique. There are varieties of optimization techniques based on the social behavior, and this is one of them, the easy technique. One can use it, right? So the collection of particles are called swarm. So particle swarm are the words used, and you see that each particle can adjust its speed. Yes, anything wrong? I'm getting some noise. Uh, I think my audio, no problem with my audio, right? Okay. Okay, let me continue. Actually, I got some sound, that's why I stopped it. Okay. Uh, each particle can adjust its direction based on its own experience and well as the others' experience. So this is the concept that has been introduced, and you see that there is only two equations. Just a minute. So is that there are only two equations to implement. Yes, so one is called the particle update rule. P is equal to P plus V, where P is the position of the particle. Right, the particle position is updated based on position, present position plus the velocity. The velocity V is determined. It is not the velocity that we use in physics or engineering. It is not associated with the time, right? It is again, it's also a position, right? So the velocity V is determined by present velocity, and it is updated by uh, two expressions, namely based on the P best and G best. P best stands for best position of the particle, right? Best position, and G best stands for best position of the swarm. So the entire swarm, which is the best position, and the particle position is best position of the particle. So based on the its own best, and based on the best of the swarm, it is get updated by random numbers and associated with the C1 and C2. So C1, C2 are weights, and usually it is kept as constant. And these are all the only two equations that is used. So position update and velocity update, right? Okay. What are the steps used in the particle swarm optimization? So first you have to create a swarm. So in order to create a swarm, you have a population of agents, right? It's distributed over. So every control variable, you know the minimum and maximum. Based on the min max, you determine the collection of particles in the range for each generated particle. So you have to create a population of particle, right? Group of particle, we call it as a population in the limits of the control variable, and for each generated particle, evaluate the objective function. Evaluate the objective function for each generated particle. So you will get suppose if you generated 20 particle set, you will get 20 objective function solutions, right? If the particle's current position is better than it, so fine, you see that so you'll create a population for each particle, you find the objective function, and we'll assume some p-best and g-best value based on that. If the current value is better than the p-best, then you can adjust. Determine the best particle according to the particle previous position, right? So these are the steps, and then after identification, you have to update the particle based on the equation. Calculate the velocity first, since you have the p-best, and right, you see that the particle update velocity is based on the equation. So now you have calculated the particle best, and you can compare with the present value, and similarly compare with the global value and update the velocity. Then having found the velocity, you can update the position, right? So this process is repeated until the all particle will get the best position, right? So this is the steps involved, and you can see this uh, this figure. I think it shows uh, just a minute, please. Okay, I'm asking for another headset. Okay, maybe in the next session we will use the different headset. Okay, please look at it. Look at this figure, and this figure shows wait, people are able to see to some extent possible. Okay. You can see that this is the pictorial representation of how particle swarm optimization works, and you see that this is the present particle position, right? And from this, how we can go particles influence memory. This is particles influence memory in this direction, right? Particles influence, right, in this direction. Current motion influence green in this direction, right? So this is this direction that is there. So from this point, how it changes, right? So you see that it can go. It will get. This is the current motions, or uh, inertia, or inherent on its own, and this is particle memory influence. So swarm influence is the red color. So when you add all, the next position. So from this position, and this is the swarm influence, and this is the green color, the current motion influence, right? So particle memory influence is this. So when you add all three vector, you will get the best or new position. So this is how it is get updated. And this shows an algorithm, right? Of this, maybe I will go to the next slide. You can see that it is exactly the same. Now you quickly see that how it has been converged, right? You can see there are green, right? Is the green color is the sorry, the black color is the particle randomly created, and it is searching for the food to identify this place. And you can see that eventually, right? So it's right. So each particle can go and finally converge to the best. This is the pictorial representation of particle swarm optimization. Now let us see how to implement this PSO in particle swarm optimization in optimal power flow, right? So I have given you the a MATLAB program for performing the optimal power flow based on ESO for an IEEE 30 bus system, right? So it is it works based on the MatPower files. So MatPower is a free open source available in the internet, developed by the Zimmerman. It's a collection of MATLAB program, and it is universally validated. All universities around the world are using this MatPower as a uh, tool for validation of their results. There is also a forum for MatPower. You can ask questions if you have any doubt in the MatPower. Zimmerman is ready to help. So I have developed and I used all my programs uh, for my PhD and also my scholars based on MatPower. So you can also use it. Let me check the audio. Nothing wrong with the audio. Okay, hello. Oh my God. Yes, yes. Hello. Hello, hello. Okay, okay. Hello. Sound serious.
Sir?
Is it okay, ma'am? Okay.
Yes, yes, sir.
No, sometimes I wanted to check. That's why I came out of the presentation.
No
So,
problem.
MatPower is a collection of MATLAB program developed by Zimmerman, and I have also given the link there. You can use the link to download the latest version of MatPower. You can use the MatPower programs to do. You can solve power flow, optimal power flow. Even there are many restructuring environment also given, so you can also try everything. There is a MATLAB MatPower guide is also available. Tutorial is there. You can use it. You can run, right? So I have used all for power flow simulations. I have used only MatPower. So I have written a program that takes MatPower and links with the MatPower. So this example shows a IEEE 30 bus system. It has 6 generators, 41 transmission line, 4 plant changing transformers, right? So I think you're able to see the flow chart in the right hand side. Okay, let me zoom to some extent so that you're able to see. Right, you see that. I think it is somewhat visible. Having the real power system data like generator data, demand data, everything, load data, you have to collect the information for the system and generate a random number of particles. The number of particles, since we are going to use IEEE system, it is there are 6 generators, so the number of particles for this system is 6. So you can create a randomly 6 numbers that represents the generator power output, and you can create different sets of these particles. So one set means 6 generators. So you can create a population size of 20. So it means you are producing a 20 sets of results. So using this, what you can do is you go for iteration. So update the weights based on the uh, equation. So you need to choose minimum and maximum values of weights. For every iteration, this weight will adjust. So it will become a dynamic weight adjustments. So we have already seen how the velocity and position can be updated from those equation. You can, until this maximum number of iterations is reached, go on adjust this particle position. So here particle position means generator output, right? So by adjusting the generator by adjusting the generator output, finally we will get the solution that the minimum generation cost is 802, and you can see that without it's a very basic PSO model. So it not is the very easy solution, or that is comparable with the other solutions also, right? So this program, what I did is I have given the link in the next slide, and you can see that there are two links available. And if you want, you can get this PPT. I have given this PPT to maybe I can give this PPT to the organizers, and you can collect this. The links, so you can just use the link that will download the two files. So it requires two files to run the program. One first file is PSO30 bus.m, it's a MATLAB program, right? Another one is a fitness function, right? So what you have to do, first you have to download the MatPower software. Then in the same folder of MatPower, you put these two files where you have case programs are there. So paste this in the MatPower folder, then run the PSO30 bus program, you get the solution. So I will show you that how the program has been written. Of course, this is the link that I have created from my system. Of course, if you touch it, won't open in your system, right? So this is the program of uh, PSO30 bus system, right? So I will give some hints, right? Just I will show you that it is the this is the entire program of PSO30 bus, and it call another function called fitness function, right? I said for this problem we have number of particle equal to 5 because there are 5 generator and one slack generator. Slack generator power can be determined at the last. You can also modify this program to include the bus voltages as a control variable. Then you have 6 bus voltages as control variable. So totally 5 plus 6, you get 11 variables. You can use number of particle as well. So this is the variable low and variable high for generator power. So variable low and variable high for each generator. It means generator 2 can have 20 megawatt as low value and 80 megawatt as high value. So these are all used to generate the particle. So I told you that C1, C2 are constants, and weights are dynamically based on this maximum and minimum value. If you want to have a better result, you can change the number of iterations, right? I assumed a particle size of 20. You can also assume any number greater than this, and you can improve the answer. So it created 20 sets of solution. So all high value I gave it as a global best. And this is the main program for each particle size, right? So for each particle size, you can see that particle size is 20. So for every particle size, what it will do is it will find the randomly create a numbers for each set between the maximum and minimum value. It will create a number, a random number generation for each value. You'll see that it's a functional evaluation. For each randomly generated number, it will find out the solution. What is the solution? This is the FN. FN stands for fitness function. You can see that I have fitness. F1 is the fitness function. Fitness function is then another program. So let me open that also. This is used to determine the fitness value or objective function. So having given the ABC constants and power flow limits of the transmission lines, then this is the MatPower codings to substitute the values of load case will load the case 30, case IEEE 30 from MatPower, and these will assign the values of that we have created randomly to the generator to get the power flow. So run PF is used to get the power flow. So run PF is used to get the power flow, and the solutions are stored in results R1, R2, R3, R4. R3 will have a generator power out. So there are 6 generator. Now we will get the generator power out of slack, and that you can verify whether it is within the limit or not. R2 result will have a generator voltages, and you can also check whether it is within the limit or not. If not, you will create a penalty for it. So it's a penalty based optimal power flow PSO. So TL is the determination of total losses. So I have created many objectives. So you can use this program for minimization of losses, or you can use it for minimization of generation cost. If you use generation cost as minimization, it will also check the power flows and voltage limit generator. Any violations occurs, the penalty is calculated. This LAM is stands for penalty, and this SIS stands for deviation from the power flow in the transmission line. So this will increase the value of objective function. If the constraints are satisfied, you will get low values. So until you will get the minimum value, this program will go on iterate. Maybe you can iterate it for maybe 100 times, you will get the solution. Right? So I think these are all the explanation for the program. So you can take your own time in seeing this. So we come to the conclusion of this. So this session has considered some history of power system, and then what is load flow, economic dispatch, optimal power flow formulations, then introduction to PSO, and then how we can implement this PSO in a IEEE 30 bus system for determining the minimization of total generation cost, right? So with this, we come to an end of first session on PSO based OPF for demand response in smart grid environment. Thank you very much. If you have any question, you can ask me, or we can go to the next session after the time. Maybe we can meet at 11:30. Thank you. Thank you for time.
Thank you so much, sir. Thank you so much for this more informative and interactive session, sir. This session was more useful for us to recollect all the things, basic things of our system and the history of our system, sir. Thank you so much, sir.
Thank you very much.
Thank you.